Good afternoon everyone, and welcome to Hewland's virtual member focus session. Hewland operates from two sites, producing 3,500 different components and 900 transmissions annually, with typical production runs from between 10 to 150 units. We also make 1,000 make-to-print components yearly. Our market sectors include motorsport, performance auto, defense, and aerospace. Our product portfolio features sequential race gearboxes, synchromesh gearboxes, EV and epicyclic transmission systems. Established in 1957, Hewland Engineering provides comprehensive design, manufacturing, assembly and after-sales services from our UK facilities in Maidenhead. In 2024, we opened a new testing facility for product qualification and R&D, aligning with automotive and aerospace standards. Hewland Engineering is also proud to be part of the Hero Motors company business, which comes with a lot of capability in high volume manufacture across various sectors. Hewland has a rich motorsport history, known for its affordable and competitive products. Historically, this relied on early customer feedback and sometimes leading to pressurized recovery situations. Now, we've built a strong engineering team to deliver the next generation of transmissions, ensuring products reach customers with a robust level of validation for reliability right from the outset. Our vision is to build the capability for turnkey transmission solutions, optimizing for weight, efficiency and durability. We aim to close the loop on design and CA validation and support new R&D, aligning with Hero's growth aspirations. Our goal is to deliver products right first time, accelerate new technology, and become a comprehensive test house for durability, efficiency, strength, thermal, NVH and shift quality testing. We will also offer innovative new services too. Our technical centre has the following test capabilities. The 3 test rig can provide up to 750 kilowatts for efficiency, thermal, endurance and gear contact testing. The loaded 2E tilt rig can run up to 500 kilowatts and is used for horizontal and vertical test orientations, covering the same types of tests as a 3E. The spin rig has a 34 kilowatt input motor and is used for lubrication, tilt testing, end-of-line spin testing and general transmission checks. Additional facilities include a thermotron chiller, 400 kilowatt battery emulation, flexible test areas and dedicated spaces for assembly, fabrication and shift quality assessment. Hewland's overall capabilities encompass design and analysis capability, production engineering, manufacturing and assembly, test and validation, and engineering services with a focus on energy management. Now, let's explore our case study, designing and testing for aerospace applications. eVTOL applications presented Hewland with a unique opportunity, requiring rapid design, manufacture and test validation for a new safety-conscious industry. This demanded swift alignment of our tools and capabilities. We applied Hewland's newly formed design and development processes using robust test feedback to close the loop on design and analysis. We'll take you through some of the aspects of the project and some of the insights we learnt along the way. Our transmission product design and development cycle systematically moves from targets definition, concept layouts, system design, detailed design, through to production engineering, manufacturing, DVP, and crucially test feedback. Hewland already have a significant amount of tools and documentation integrated throughout our process. The aerospace sector relies heavily on strong documentation and traceability, along with robust mitigation processes. We improved and updated our process and procedures and now have AS 9100 certification. While our existing design and development process covers many aspects, key differences for aerospace included detailed requirements capture and compliance tracking, increased safety factors, and the method of qualification for durability. Further distinctions were in flight hazard analysis, preliminary safety system assessments, safety of flight declarations, and paramount was the traceability of components and materials. Master was used to generate and compare multiple layouts based on durability, weight, packaging, and efficiency. We assessed spur and helical gears for potential weight reduction. Crucially, tooth count and ratio selection was used to balance bending and contact durability, considering contact ratios for MVH, torque density, and efficiency. We carefully selected individual ratios to avoid overlapping frequencies and prevent excitation of natural frequencies within the operating speed range. For bearing selection, our focus is the right bearing in the right location to react loads and potentially downsize. For planetary systems, spherical roller bearings were found to improve load sharing. The visuals here demonstrate avoiding frequency overlap by discounting problematic tooth numbers. In detailed gear analysis, we optimize gear web profiles to reduce misalignment, helping to support the microgeometry design and potentially reducing weight and face width. A key aspect is ensuring gears can be used in both clockwise and counterclockwise transmission systems. For gear microgeometry tolerance analysis, Taguchi arrays were used to generate candidates, followed by parametric studies in master to ensure optimal performance across manufacturing tolerances. Finally, we reviewed stock allowance and case depth to prevent through hardening. This slide illustrates using a Taguchi array for candidate generation and early FEA in master, providing critical insights like weight increase and significant misalignment reductions. For detailed bearing analysis in master, we conduct comprehensive bearing fit and internal clearance checks to prevent radial preload under all operating conditions. We also review oil candidates, assessing viscosity ratio to ensure adequate film thickness, assessing bearing damage to ensure no adverse impacts to fatigue life, and we also review gear scuffing and micropitting. Continuing with bearing analysis, we review bearing stress and misalignment for different raceway profiles, especially in extreme misalignment scenarios. The visual shows bearing stress distribution for various oil candidates. To ensure safety of flight, conservative stress targets had to be met. All parts had to be designed with significant safety factors against yield and UTS, as well as for infinite fatigue life. The casing was the most challenging part because of the complex combination of applied loads and conservative stress limits of the magnesium alloy. Stress limits for the casing were derived from a combination of accumulated fatigue, knockdown, and casting factors. The magnesium alloy was chosen for the casing because of its low density. However, the factors applied to the endurance limit was challenging at 17 megapascals. A detailed FEA model was created for the complete casing assembly and its connection to the airframe and electric drive unit. The model was set up with multiple load cases to allow comprehensive stress and fatigue assessments to be performed. Through multiple iterative design loops and close cooperation with the customer, we were able to achieve a design that satisfies safety of flight. A lesson learned is that the increased structural mass added to meet fatigue targets actually offset any benefit of choosing magnesium over aluminium. Keeping the total weight of the gearbox within the required target was key throughout the design process. Detailed, weekly, up-to-date mass records were kept, showing the contribution from individual components. To meet other targets, structural mass often had to be added to the components. This required the need to look at mass-saving opportunities across the transmission system. Design and analysis activities investigated opportunities for reducing mass. This included investigating novel designs for the gear webs and the use of structural optimization techniques. For all bolted connections, best practices and the VDI 2230 method were followed to ensure the integrity of joints. To support these traditional calculation methods, detailed bolted joint representations were included in FEA models. Both methods ensured robustness of the connections. Complex joints often required more in-depth studies. One such example is a large retaining nut on the mast shaft, for which VDI predicts a high embedding loss. The resulting prediction in preload would lead to a risk of joint separation. For further investigation, leveraging additional calculations and analysis in-house experience concluded any loss in preload would be minimal. To close the loop, a retightening procedure was put in place, which confirmed that conclusion. Next, our approach to oil management and optimizing oil circulation involved extensive analysis using ParticleWorks software. Through ParticleWorks, we conducted rigorous optimization studies for various flight orientations, which included pitch, roll, and cruise. Iterative design and analysis loops allowed us to design effective baffles. These baffles optimize the dynamic oil level, reduced captive oil volume, and efficiently redirected oil back to the sump. This significantly reduced initial oil hang-up around the gear train by strategically capturing and redirecting it. The philosophy of gear and bearing durability testing differs significantly in aerospace. Our gearbox was designed for a 250-hour mission profile, but most rotor drive systems follow either Part 27.923 100-hour or Part 29.923 200-hour of the Code of Federal Regulations. For this demonstrator vehicle, with limited flight aspirations and under extreme monitoring, Part 27.923 was chosen as the more appropriate shorter test. We still wanted to understand the expected damage levels for this 100-hour endurance test for our application. This 100-hour multi-block test resulted in only 52% damage to gears and 49% to bearings, meaning no observable damage could be accepted. Post-test, all gears underwent nitrile etching and were regraphed. Casings were dye-penetrant tested. Our DVP approach ensured we only advance after fully characterizing and understanding each component and subsystem before we move on. We credit Hofer Powertrain for being able to use their facilities for the early component and subsystem tests while our new Southern Technical Centre was being completed. Subsequently, we performed gear contact, thermal stability, durability and loss of lubrication tests at our technical centre. For the ship sets, a short end-of-line test was devised for shakedown, followed by a semi-strip down, inspection, cleaning, filter replacement and a reassembly before shipping. 3 test units performed the basis of our test development and validation plan. We covered component and subsystem tests such as pump flow rate, PRV checks, mast bearing oil flow checks, jet direction and flow checks, clear casing baffle development, and gear contact testing. We performed functional tests, including torque to turn, efficiency, and MVH performance. We then moved to the full system durability tests, covering gear and bearing durability, high-speed thermal, and loss of lubrication. Extensive lubrication tests were conducted to evaluate oils across high and low temperatures. We applied a range of oils with varying viscosity characteristics to get indicative performance feedback across different simulated temperatures. The chart illustrates the performance of various lubrication oils against temperature. The TUI loaded tilt table was indispensable for durability testing, enabling tests in both lift and thrust orientations. we followed stringent processes for the rig's design and setup to ensure accurate alignment to give reliable durability results. Crucially, torsional modes of the complete assembly were calculated to prevent excitation within the gearbox's operating speed range. During testing, continuous monitoring assessed gearbox performance, including oil temperature and RMS accelerometer data. FFT analysis of accelerometer signals allowed further interrogation of responses at specific forcing frequencies. Strip-down tests were performed at midpoint and completion. A critical loss of lubrication test was also conducted using specialized shafts to contain damage if seizure occurred. However, the gearbox successfully passed the requirement to be run dry, demonstrating exceptional robustness. Key learnings from this aerospace program include aerospace lead times. Suppliers built in longer lead times for conformance certificates and full traceability. This had a massive impact on our program timing. Casing material. Magnesium's initial weight advantage was offset by the extra material needed for strength and fatigue resistance due to the high safety factors involved. Traceability. This required a significant cultural and operational shift, necessitating new processes within Hewland. CAE. Approaches had to be specifically adapted for aerospace methodologies, especially concerning fatigue and complex bolted joint calculations. And some further learnings. Closing the loop on requirements capture via a robust validation and verification matrix was vital to confirm every requirement was met by analysis or by test. Ultimately, open and proactive collaboration with our customer was key to overcoming challenges and delivering a successful program. At Hewland Engineering, our mission is to design, manufacture, test, and innovate reliable, efficient gearbox solutions. Beyond design engineering, we add significant value through manufacturing performance services. Backed by Hero Motors Company, we can scale from low volume to high volume programs, offering our customers full turnkey gearbox solutions. Now, let us listen to one of our recent aerospace customers describing their experience of Hewland.
The Hewland team from programs, engineering, manufacturing and quality were a top-tier supplier for the prototype program. Hewland was able to deliver a high quality of work and product in a compressed timeline while seamlessly adopting aerospace-grade processes, particularly in manufacturing quality and material traceability, demonstrating a strong commitment to excellence. Hewland's ability to iterate on innovative design solutions and quickly adapting to structural criteria, whilst also navigating the complexities of aerospace analysis, was truly impressive. Throughout manufacturing and testing, the team responded swiftly to anomalies, conducted thorough root cause investigations, and kept progress moving, even under challenging circumstances. Throughout the project, the Hewland team provided timely updates, worked diligently to meet requirements, and collaborated effectively to resolve issues. Their top-down capabilities from design, analysis, manufacture and testing enabled Hewland to execute the gearbox program at a rapid rate to support the overall aircraft program goals and timelines.
Let's outline Hewland's current and future value to our customers. Currently, we offer clean sheet gearbox design and analysis, prototype manufacture, low volume series production, make-to-print services and extensive testing. Looking ahead, our future includes medium volume series production via Hero Motors and enhanced engineering services focusing on energy monitoring and manufacturing optimization for sustainability. Our future service roadmap also includes consortium-based testing, EDU testing, a spin rig with 2-axis testing including automation, and part brake testing. A key future service is sustainability and energy monitoring. Hewland is committed to reducing our carbon footprint towards net zero. Energy monitoring of our manufacturing facility is crucial for reducing consumption, improving productivity, and cutting costs. Hewland's dedicated sustainability team have implemented activities to reduce carbon footprint and grow towards net zero emissions. A key initiative for reducing energy consumption, improving productivity and driving down costs is our real-time energy monitoring of the Maidenhead manufacturing facility. Combining the energy data with live up-to-the-minute production information allows key performance metrics to be calculated. The metrics help to identify opportunities for cost saving and process improvements, and once implemented, the impact of these actions can be tracked. Using a combination of specialist monitoring equipment and tailored software, we can provide similar actionable insights into other manufacturers' facilities to enable them to make smart, sustainable changes to their production. The outputs from the energy monitoring include a detailed breakdown of energy cost and time to manufacture each part, as well as daily reports on machine utilization and downtime. Visualizations help identify cost-saving opportunities by tracking energy consumption and manufacturing time as a work order progresses through the factory. A precise breakdown of the energy cost is calculated at each operation, and actual factory time is compared against scheduled time. Hewland are currently working with Hard Drive Limited on a research proposal to perform a life cycle assessment on a gear. The proposal will soon be submitted to the BGA for approval. Key to the accuracy of the life cycle assessment will be the data captured and interpreted by our energy monitoring equipment and custom software. Thank you for your attention. Our Hewland team will be happy to answer your questions.